Good afternoon, everyone. I am Sergio Burdizo, one of the members of the team from Argentina. First of all, we are really sorry because we were not able to be present at this great event in person due to our country's current economic situation. However, we thank the organizers for letting us introduce our work to you through this video. We are going to present our proposals for both tasks of the eRisk 2018 Lab Challenge for early risk detection, which are early detection of signs of depression and early detection of signs of anorexia. Namely, we are going to briefly describe two methods that we have called flexible temporal variation of terms, or FTVT for short, and sequential incremental classification, or SIC for short. We are also going to talk about the experimental settings used for tuning our classifiers, and we will show the obtained results for both tasks. Finally, we are going to present our conclusions and talk about possible future work. First thing first, let us introduce ourselves. We are a small group of people which try to compensate the lack of economic resources with great passion. We all work at the LIDIC laboratory, which is located at the Universidad Nacional de San Luis, or in English, the National University of St. Louis. Our university is located in San Luis, the capital city of San Luis Province, or state. San Luis is a small and beautiful city located right in the center of Argentina. Now that we have introduced ourselves, let's begin describing our work on the last eRisk competition. As mentioned earlier, our proposal to address both tasks this year was based on two completely different approaches. Flexible temporal variation of terms, which is basically an improvement of the tivity method presented last year, and sequential incremental classification, a novel and simple approach for early risk detection tasks. Flexible temporal variation of terms is a semantic representation of documents that explicitly considers the partial information that is made available at different chunks over time. As presented for the first time in the eRisk 2017 challenge, temporal variation of terms is a document representation derived from concise semantic analysis, or CSA, which copes with the well-known drawbacks of bag of words. Namely, its sparse and high-dimensional vector space, and additionally, the absence of relationships among words. CSA interprets words or documents in space of concepts that is usually equal or similar to the category labels. For instance, in case of depression or anorexia detection, CSA would represent documents by two-dimensional vectors, one feature for each category, for example, one for depressed and other for non-depressed. Our flexible tivity extended CSA by considering the positive class as composed not only by full documents as in standard classification, but also by partial documents provided at different chunks. It's worth mentioning that the number of chunks must be specified in advance and may vary according to the needs. That's where the word flexible came from. As an example, suppose we want to consider only the first 4 chunks to represent documents. Then, when working with flexible tivity, each document would be represented as a 6-dimensional vector, 1 dimension for the negative class and 5 for the positive class, 1 for the full document and 1 for each of the 4 chunks. Now that we have talked a little bit about flexible temporal variation of terms, we would like to highlight some of its virtues. FTVT is a method that showed us to be quite robust and stable, given that, to work properly, it does not require any external resources of any kind, such as ontologies or custom dictionaries, or any elaborate feature engineering techniques either, such as handcraft feature extraction. Additionally, it naturally copes with the class imbalance problem, and it has a low-dimensional representation space that explicitly represents temporal aspects of the domain. However, one weak point of flexible tivity is that the number of chunks needs to be specified in advance, which means that the number of chunks is a hyperparameter of our model. Sequential incremental classification, or SIC, is a novel supervised learning model that is well suited for early risk detection tasks. The method's formal definition is currently under reviewing process to be published in the Expert Systems with Applications journal. However, SIC basically uses word frequency stored during training stage to compute a value using a function we've called global value, or GB for short. The GB function gives words a value in relation to categories. That is, it takes a word in a category and outputs a number between 0 and 1 representing the degree of confidence with which that word is believed to exclusively belong to that category. It is worth mentioning that to compute global value, we make use of other two functions, local value and weight. The first one gives words a value based only on the local frequency of the word in a given category. And as part of this process, the word distribution curve is proportionally smoothed by the sigma hyperparameter. The second function decreases its value in relation to the local values of the word among all categories. The more categories whose local value is high, the lower the weight value. As a side note, the lambda hyperparameter allows us to control how subtle this relationship is. Finally, classification was carried out by means of the cumulative sum of all words over all available chunks. So, a subject was classified as depressed when the accumulated positive value exceeded the negative one. For instance, the subject in this figure was classified as depressed after reading the fifth chunk. Sequential incremental classification's strong points are: it is a very robust and efficient classifier for early risk detection tasks. It supports incremental training and classification of sequential data. It is a general-purpose white box classifier that allows interpretability of results. Its domain-independent classification does not require feature engineering or complex rules to decide when to classify subjects. However, the main weak point is that it requires two hyperparameters to work, sigma and lambda. Now that we have briefly described both approaches, we are going to talk about the experimental setting. For FTVT approach, we performed an experimental study in order to fit the hyperparameters for the provided datasets. Firstly, we carried out a 5-fold cross-validation, only on the depression training set. Then, each fold was divided into 10 chunks and documents were randomly selected, maintaining the same proportion for both categories. As we mentioned previously, to use FTVT, a decision must be made related to the number of chunks that will enrich the positive class. So we consider n ranging from 0 to 5. FTVT was then evaluated with logistic regression and support vector machine, among other machine learning algorithms. For this step, we made use of the classifiers provided by the scikit-learn package for Python 2.7 with L2 penalty and C constants equals to 1. Lastly, we used the probability assigned by the classifiers to decide when to stop reading and classify the subjects. That is, when the probability assigned to the positive class exceeds some particular threshold, the subject is classified as positive. We adopted 4 different thresholds: 0.9, 0.8, 0.7, and 0.6. UNSL was meant to minimize the ERDE5 error, considering that it's more restrictive but accurate. On the other hand, UNSL V and C were meant to minimize the ERDE50 error, given that they are more permissive. With respect to seq, no hyperparameter optimization was done, and therefore hyperparameters were manually selected for both tasks. Sigma was set to 0.5 for both UNSL D and E, and lambda to 3 and 7 for UNSL-D and E, respectively. UNSL-D was meant to be less sensitive than UNSL-E on penalizing words, and as such, it considers more words as being important, hence favoring UNSL-D to have a higher recall with the risk of having a word's precision. Now it's time to show the obtained results. For the depression detection tasks, we can observe that UNSL-A using FTVT obtained the lowest ERDE5 error, which was 8.78%. The same can be observed for the anorexia detection task, in which UNSL-V had an ERDE5 error of 11.40%. Additionally, SIG obtained a remarkable precision on anorexia detection, namely 90 and 81% of precision, which was the highest among all participants. These results show strong evidence that both approaches are interesting alternatives to deal with early risk detection tasks. To conclude, we mostly see positive aspects to highlight. We used two completely different approaches to deal with both tasks: flexible temporal variation of term and sequential incremental classification. Both approaches showed us to be quite effective on both tasks, obtaining the best ERDE5 values and the best precision value for the anorexia task. That's quite impressive, having into account that they are completely domain independent and that, although it is true that FTVT's hyperparameters were selected only for depression, they also worked remarkably well for anorexia. Another important point to highlight is that neither of both methods require a costly or manual process of feature engineering. The obtained results suggest that both methods are quite robust despite of using a very simple rules to decide when to classify users as positive. For further research, we plan to extend the use of FTVT and SIG to other early risk detection problems, such as early rumor detection, identification of sexual predators, or people with suicide tendency, among others. Finally, we want to thank you all for your attention and for your time. For more details, you can check out our paper or you can contact us by email for specific questions.